So let's just consider for a moment what is a conformal coating. Well, IPC's definition of a coating is defined as a thin, transparent polymetric coating that is applied to the surface of a printed circuit board assembly to provide protection from the end-use environment. And typical coating thicknesses range between 12 to 200 microns. So let's ask the question now, why do we want to conform or coat a printed circuit board assembly? And there are a number of different reasons why we may wish to do this. First of all, prevent premature failure of a product, and this can be corrosion, it can be erosion, or it can be a chemical attack, or it can be some form of electrical failure because moisture is getting to the surface of a printed circuit board. In some instances, we're starting to find, with more sensitivity of circuits being used on modern portable products, that people are using conformal coatings to maintain or enhance a particular section of the printed circuit board or a particular component's functionality. So localized coating provides some benefit there. Improved environmental protection is probably the most common reason that's stated for the use of conformal coating. It's also an alternative to a sealed box environment. Rather than actually putting a product into a sealed box, we have the ability perhaps to coat the product and then not actually using a sealed enclosure. And this may actually reduce the cost of the final product. In some cases, some materials are actually used to help ruggedize the assembly. So where we're looking at thicker coatings, they may actually give some form of mechanical support to small components during the operational life of the product. However, generally speaking, when we talk about much thicker coatings, we're really talking about potting as opposed to coating. And there obviously is a difference between these two forms or medium. One of the important things is you should never use a coating to overcome a problem unless you know what the problem actually is. So if it's a failure because of corrosion, the environment, vibration, make sure you understand how the product has failed, why it has failed, before you consider coating. A lot of people miss this point and introduce coatings inappropriately for their particular product. Briefly, let's look at the options. Now, I've listed here on the left-hand side the general coating materials or coating families that are used in the industry. By the side of that, we've got a designator, and these are the designators that come out of the IPC 830 specification. And these are abbreviations also for these types of coatings. And by the side of that is a typical guideline to the thicknesses of coatings that might be applied by any one of these coatings. It will of course depend on the material, the solids content, the method of application to the printed circuit board assembly, but these are general guidelines on thicknesses that may be achieved with any one of the particular coatings. There are quite a lot of resources available in the industry for conformal coating, and it's important to sort of gain as much information as you possibly can. I've listed here all the documents that are generally available, the IPC, the MIL standards, the DEF standards, and also one publication or book that goes into different types of coatings by James Licari. And if you do a search online, you'll be able to find a copy of that publication. Another document that we'll refer to a little bit later on is the NASA workmanship standards for conformal coating in printed circuit board assembly. And this is a document that is freely available online. You just have to do a Google search for it because it's hidden away somewhere on the internet. But you can find that, and there's quite a few pages that relate specifically to conformal coating, and it's quite a graphically well illustrated document. Another source of information is some wall charts that I've produced, and these are colour standards for inspection and quality control of conformal coating. These are often used on my own hands-on workshops, and they're generally about 24 sheets which make up a good reference standard. Two of other things we've recently introduced with the IPC and the SMTA in America is an interactive conformal coating CD-ROM and also a photo CD, allowing you to create your own training material. So before we go any further and we look at inspection and quality control of the process, let's pick up on just the two basic processes that are most common in our industry today. We've already seen from the graph that we've produced that the dip coating process is probably one of the most common used when we're talking about a semi-automated process. And basically, dip coating, we're taking a printed circuit board assembly which can be held vertically as we show in the illustration, and then is lowered into a container full of the coating material. The board remains below the surface, and a good guideline to make sure that the coating is penetrated and there's no air entrapment is to just look at the bubbles that are coming up through the fluid on the surface. And by experience and also examining boards after the coating process, you can judge the time, the dip time in the material. It's also affected by the viscosity or the solids content in the conformal coating material. And by doing trials, you will see and maintain, or be able to maintain the thickness coatings on the surface of the board. The way in which and the speed at which the printed circuit board is drawn out of the bath of coating will also affect the quality, consistency, penetration, and the coverage on some of the sharp edges. In dip coating, generally speaking, depending obviously on the parameters I've already mentioned, you get a thicker coating. However, if you change the viscosity of the material or one of the other parameters, then you may change the thickness of the coating. The key thing with dip coating is that obviously correct masking has been conducted on the printed circuit board on component areas that mustn't be coated. The alternative to dip coating, becoming more popular, is spray coating. And when we talk about either manual or semi-automatic spray coating, we're talking about a one-sided process. So basically, we're spray coating across the surface of the printed circuit board and coating the whole of the surface of the board in multiple strokes. In this situation, it is obviously dependent on the speed, the nozzle size, the height of the nozzle above the surface of the printed circuit board, and again, of course, the materials that are actually being used. One of the benefits of automated coating is that we can program the dispense nozzle or dispense system to selectively coat certain areas of the printed circuit board, and this allows us, provided there is enough gap tolerances around components, to virtually eliminate masking. It's very difficult to totally eliminate masking, but it's something that we can nearly achieve with this process. If we're doing double-sided assembly and we're going to use spray coating, then of course we have to do one side, and then we would have to turn the printed circuit board over to allow us to do the second side. Of course, with the dip coating process, you'll be conducting this on both sides simultaneously. You would not be able to lower the board horizontally into a dip coating process and then lift it out, because the variation from side 1 to side 2 would be quite dramatic. So what is the actual sequence of assembly? or the actual sequence of the coating process? Well, first of all, we clean the board assembly. So what do we actually have to do? Well, that depends on your product and your application. Cleaning the printed circuit board assembly is a common process with conformal coating. However, it's not necessarily mandatory, and you have to decide. If you take a lot of automotive manufacturers, the majority of those do not clean, however they do conformally coat. However, they must engineer their process to minimize the amount of contamination which is present from any previously soldering operations. The next step is masking selected areas depending on the design of the printed circuit board, and then we would coat side one of the assembly, possibly allow the board to dry or touch dry prior to flipping the assembly over. If it's an automated process and you're spray applying the coating to the surface, then you would probably flip the board assembly over and continue coating the second side. Inspection needs to be conducted at some point, and sample inspection is good, but remember, obviously the board is either wet or tacky, so consequently it must be a non-contact method. Next up is there's a hold time, and we're holding the board assembly in the case of solvent to allow the solvent to evaporate off. If you start to dry or cure the conformal coating or a conformal coating prior to this operation, then what you'll tend to do is create defects, and probably the most common defect is bubbles in the coating due to fast curing. Then we have the curing process as defined by the supplier prior to final inspection. And our conversation today is really related to inspection and quality control of coatings and coating processes. So the first thing we need to do, or we need to make sure happens, is that in the factory everybody has an example of the printed circuit board, or a drawing or an illustration of what needs to be coated and what areas must where coating must be avoided. And this obviously stems back to the original design. So it may be a drawing, it may be a photograph, it may be a golden board. So in this example here, on this board, we may say that the edges of the board need to be clear of coating. And the reason may be that we want to put this in a card runner, mounted in a box assembly, and contamination by conformal coating on the edges may make it difficult to put in place. Alternatively, with high-end, high-reliability products, sometimes the core of the board is used for heat dissipation. So we're actually using the edge to take heat out of the assembly. So consequently, that's a reason whereby the coating must not be applied. Other areas may be, in this example that I show, this illustration, a trimmer capacitor, which I've highlighted, and also on the edge of the printed circuit board assembly, we've got a connector, which I'm illustrating here. Now, a key thing is that we may be using this as voltage in, voltage out, so it may be very important to make sure the terminations are protected by conformal coating, but it's an issue, and has been an issue for some time, to also make sure the body contact, or the contact between the pins and the plastic, doesn't allow capillary action and allow the solvent or the conformal coating to penetrate up through the connector interface. Now, if you're going to selectively coat the printed circuit board, perhaps the areas I've illustrated now are the only ones you want to coat. Well, there's going to be a lot of masking operation needed if you're going to dip coat, but with spray coating selectively, you may be able to achieve this and not coat other areas of the printed circuit board. Again, it depends on your system and the results from your trials, but you must have some basic reference, and also if you're subcontracting out this product for coating, then it's very important to make sure that you give this information to your supplier. So there should be a drawing, a photograph, or ideally a golden board. So now let's just look at some of the failure modes of printed circuit board assemblies. And the first one I show is dendrite formation. And basically in this photograph you can see examples of dendrites, and what this is copper corrosion product. And basically what is happening is we're getting a plating cell between one surface and another, and what you see here, the black area, basically is a copper growth, a copper dendrite, and it's quite a common failure mode that's seen on printed circuit board assemblies. And if we just jump to a video clip, we should be able to see this in real time. And basically the video clip illustrates the dendrite formation. And what I'm showing you here is dendrites forming between two conductors on a printed circuit board assembly. And this is in real time. It's in real time. However, because there is quite a large droplet of moisture on the surface of the printed circuit board, this is the reason that it's happening quite quickly. In a normal situation, this may take weeks or even months to actually form. Another example is white residues and corrosion products on the surface of a printed circuit board. Again, white residues quite often are not harmful for the product, but if it's a combination of the white residues and the dendrite formation, then clearly this may be an issue. CAF is another failure mode which can happen in a printed circuit board assembly, but this is an internal defect, and certainly conformal coating would not necessarily stop it happening. Another example of cracking and chemical reaction is illustrated in this photograph, and what has actually happened here is something underneath the coating has allowed a reaction to take place, which has then caused the conformal coating to actually crack. And in that situation, obviously, the coating is lifted from the surface of the printed circuit board, and a reaction has taken place, and this will continue to occur. This example photograph shows verdigris. This is a green corrosion deposit, and normally seen on copper and copper materials, and normally is a reaction based on the flux residues left on the surface of the board. If you've got some reactive materials which are left on the surface of the board, verdigris can form. However, generally speaking, it looks worse than it actually is. And finally, the final illustration, the final photograph, shows all three in one place at the same time. So we've got white residues, we've got copper dendrites because of moisture and applied voltage, and corrosive materials and verdigris, all three in one place. One final thing I wanted to mention, and this is something that's come up recently in the last few years, where people have been using silver finished printed circuit boards. And silver finished printed circuit boards, there's not a problem with using silver, but silver in combination with exposed copper in a sulfur environment can actually lead to corrosion. And what I illustrate in the photographs here in this area, corrosion has taken place and actually eaten through the track and pad interface. The X-rays below it also show the same thing, and you can see what appears to be mouse bites in the surface of the copper, and in time these would go all the way through. In the bottom photograph you can see corrosion products actually starting to span between two pads and two terminations on an SOIC. And this is to do with sulfur in combination with silver and copper surfaces. And finally, just an example of a BGA, a ball grid array, and you can again see, using an oscilloscope or similar equipment, you can see directly underneath the package the black deposit which is starting to form between two closely spaced conductors. Okay, so that's some of the failure modes. Now finally I wanted to mention one other process, conformal coating process, and the reason for mentioning this is it's considered to be the Rolls-Royce of coatings. However, it's not appropriate for every application. It's an expensive process, but it is unique in that the coating is defined very tightly because of its process. And basically, vacuum deposition, or the parylene coating, we're putting a board assembly into a chamber, and what is actually happening is a gas is condensing onto the surface and forming the coating. So actually, as opposed to spraying or dipping, we're actually using a vapor transfer process to produce a coated printed circuit board assembly. Normally this is always contracted out. It is not normally an in-house facility. And I've shown you here three examples. Three photographs on this slide illustrate a board that has been coated with parylene. And in all honesty, when you look closely at the surface, you really can't tell that it's actually being coated. It takes a lot of experience, and I, for one, find it difficult. So on the top left-hand view, you can see a board assembly. On the right top view, you can see a close-up of a solder joint, and really there is no obvious sign of a coating being present. However, in the third view, the microsection view, you can see the coating is quite clear as a grey line around the part. And the interesting thing with this coating, as I said earlier, because it's applied as a vapor process, it is absolutely consistent. So if you define the process and you want, let's say, 10 microns, 15 microns, or 30 microns, then that is what you will get. So you will have that consistently on all surfaces. However, because it's a vapor deposition process, the masking of areas that must not be masked must be absolutely perfect. If there are any gaps, any apertures which allow the coating to penetrate, it will penetrate and contaminate those surfaces. Because it's difficult to actually see, one of the quality control processes that we use is thickness measurement on a sample, label, a piece of card, a glass slide, and in this particular view I show a machine, a spectrometer, being used to assess the coating thickness on a test strip. And this is something that might be used as a quality control aid for inspecting the quality of control and consistency of the coating. So, as an illustration of some coated printed circuit boards and some of the joints and what they may look like on a printed circuit board assembly, as I said previously, I quite often use quality control charts for illustrating this. And what I wanted to do is just show a few examples of joints that have actually been coated, and just to give you an idea of what to expect when we talk about inspection and quality control. Now, first of all, I show you some individual joints that have been inspected under ultraviolet light. As we'll hear a little bit later on, ultraviolet light is something which is important as an inspection and quality control technique during conformal coating inspection. And I'm showing an SOT23 which has been coated. It's being inspected under a UV light, and the photograph illustrates perfect coating, consistent coating. The next illustration is a simple capacitor on a printed circuit board assembly. And again, we're inspecting this under ultraviolet light, and you can see that that's apparent around all of the termination of the device, on the surface of the board, and also on the top. Now, a lot of people say that the intensity is an indication of the thickness, and in some cases that is true. So when you're looking later on at complete board assemblies, then the intensity of the glow gives you an illustration of the thickness, but you cannot use that as a total guide. Another photograph that I show here shows an SOIC, and again we've coated the printed circuit board, and you can see the conformal coating over the surface of the terminations, the body of the part, and also between the individual terminations on the board. And for conformal coating to work, the most important area obviously is between electrical terminations. So this is a critical area to do your inspection to make sure there are no defects which do not allow a insulative coating to be present. A couple of sideways view, if I may. This photograph shows you a sideways view of an SOIC. It could be a QFP, but just a gull wing termination. And again, you can see how the UV coating fluoresces during inspection, which allows you to gain an idea of the coating, and if the coating is present around the terminations, underneath the terminations, and on the body of the device. And just another view here to show you a similar termination, but on a smaller device with smaller gull wing terminations. In all honesty, you are not going to inspect to this level. You are going to do a general inspection over the whole of the board assembly. However, you still need some sort of inspection and quality control reference when you do investigation. So if you find a defect or a blemish you want to look in more detail, then you should still have some sort of reference standards to allow you to inspect. So that's just an example of some typical solder joints. And what I wanted to do now is show you some, again, solder joints, but show you some solder joints that have actually been microsectioned. And this is one of the techniques which can be used to assess the thickness of the coating. And this would typically be used when you're verifying a process, when you're initially setting it up to get a feel of the performance of the coating process you're using, the material, the solids content, and also the difference in surface, where you're coating sharp edges, flat surfaces. So in these four examples, I show the coating after microsectioning on terminations. If we just have a quick look, here you can see that the coating varies quite a bit. So on the surface of the board, the coating is quite thick, and as we go up the side of this capacitor on the photograph, on the left-hand view of the screen, you can see quite a variation in thickness. If we move over to the photograph on the right-hand side top of the screen, the actual coating again varies quite a bit in terms of thickness, and right on the edge of the plastic device where there is a sharp corner, you can see the coating is quite thin. And this is typical of all conformal coating processes. And if you have some sharp points or some sharp terminations on something that you're going to be coating, you may well have to consider coating that particular part or that particular assembly twice to guarantee you have an insulated coating in that particular position. So inspection, how do we do it? What do we need? What do we do? Well, first of all, the most common form of inspection is a UV booth, and this can be something that you can purchase. The price will vary somewhere between £1,000 to £1,500 UK sterling, and you may have extraction in the booth. If you're going to do any touch-up or rework, you will have a UV light source, and you will obviously have it fixed on a bench at an appropriate height to allow the inspector to inspect the assembly. Very important. Ergonometry is very important to make sure that somebody is comfortable during the inspection phase of this particular process. There are a number of suppliers of these pieces of equipment. It is fair to say that some companies have even made their own as well. Now, when you're doing in-process inspection, perhaps when you're doing audit inspection in manufacture, it's useful to consider buying yourself a UV torch, a UV light. I have one of these. I use it myself, and surprisingly is very, very good for sample inspection if I'm at a customer or if I'm just doing sample inspection on the shop floor. It's enough to illustrate a good, successful coating process. On the right-hand side of this slide, I show a photograph of a well-known, commercially available inspection system which has been fitted with a UV light source. And basically the UV light source allows you to inspect the board in a similar way that you might do with the UV booth, but at higher magnifications. And you have to decide what you actually require. Generally speaking, when you're using a microscope or a higher magnification, you're doing investigation. You're generally not doing board-to-board inspection. That is normally conducted under a UV source, perhaps in a booth. That's general inspection, first level inspection, I would suggest. Now, as we move from small, medium volume production, there's been an interest in the last couple of years to automated inspection, and automated systems are available in industry. I show one example of a benchtop inspection system. There are a number of suppliers out there that offer AOI systems for conformal coating inspection, and basically they're using a UV source. They're using their same software but developed algorithms specifically for inspecting board assemblies. Now, you can use benchtop systems or inline systems. Again, talk to the well-known suppliers about their capability for board inspection. But don't be misled. This will take time to set up, just like any other AOI system takes time to set up for general solder joint inspection. But again, evaluate the materials and the suppliers, the degree of fluorescence, and the ease of programming the systems. So I show an example of a typical board assembly which has been coated, and this is the view that you might see during AOI or automatic inspection of a board assembly. And the next view just shows a close-up of an area which has been inspected and where the software is being defined to say what is acceptable or is unacceptable on a printed circuit board assembly. So again, this doesn't come all pre-programmed in, meeting the requirements of your particular inspection criteria. This is something that you need to do yourself. So you're teaching the assembly what you like and what you don't like. Moving on to the more practical side of the inspection and quality control. And I've listed here some things to consider. First of all, coating material, quality and suitability. Now, that's really outside of the control of production staff and engineers. It's probably been defined by design or development groups. But it's important that when you've got the materials from whichever vendor you're going to be using, that you make sure you store them, control them, and follow the material manufacturer's recommendations. And they will define what needs to be done to get the best out of the materials and also to maintain the materials at a suitable standard. Process control of materials and application, just like any other manufacturing process that we use today, it's important to pick selected parameters to monitor. And you're not monitoring possibly on a daily process. You may be doing this once a week, once a month, but monitor the performance of the process against your quality levels. Board surface preparation, cleanliness, solder mask type. Again, you've got to decide whether you're happy with a coating being applied to an unclean board, but again, it is not uncommon practice to do this. But also, one thing that a lot of people forget about is the solder mask type. Solder mask varies from supplier to supplier because there are different materials in the industry. So the adhesion of your chosen coating to a mask is probably one of the biggest problems that industry face. And I'm not saying this is a bad thing, it's just a fact of life that many people never define the green stuff that's on the surface of a printed circuit board. You have to have some form of inspection of the board assemblies and have standards, and I mentioned right at the very start of this webinar about having good photographic standards or golden boards or producing your own, and make sure that's good feedback. Having worked in quite a few conformal coating facilities, a lot of people do a very good job on coating, and then when the boards go out for inspection, either internally or externally to customers, they're rejected because all the different departments are working to different rules. They shouldn't. You should all work to one standard that is agreed for the product. First of all, in terms of cleanliness, most engineers are quite familiar with monitoring cleanliness, and basically if we're checking cleanliness of a board assembly, this is conducted using an ionograph or similar equipment, and we're actually measuring the cleanliness of the board based on the change of resistivity or conductivity of a test solution, which is a mixture of alcohol and water, either 75%, 25% water, or 50% alcohol demineralized water. And there are standards for the level of cleanliness of a board assembly, and this is a judgment for ionic contamination on a board assembly. So that's pretty standard practice in our industry. Another technique which is used, but normally in process development, is SIR, surface insulation resistance. And what we're doing here is confirming the consistency and quality of the test boards and board assemblies after going through a number of different processes. And what you're seeing here is a rack of my boards sitting in a test chamber after they've been connected with a voltage, and we're monitoring the changes in surface insulation resistance on the sample. Now today, fortunately, this can all be done automatically, and on the next slide, this graph actually shows you the results that you might get after processing a special test coupon. And you're looking at the voltage resistance over time, and what you're seeing here perhaps is that the blue line illustrates a failure. We've subjected the board assemblies to a hostile environment, and we've seen a drop in the insulation resistance, and it's not recovered at all. The green line, the light green line, where you're seeing a little blip, perhaps is an area which might be questionable on one of the test coupons, and perhaps the rest of the test results you're seeing are satisfactory. Again, you set your criteria based on international standards, but this is a measure of the performance of the whole process, so that all the materials, the coating, etc., under adverse conditions. So let's look at now some practical things that we can do in terms of inspection and quality control in our process. First of all, simple process checks. We can do thickness measurements with wet film gauges, and this is a simple thing, and when we can compare the readings we get with the readings of the board after the curing operation. The reason being that when you're applying a coating to a printed circuit board, the carrier will evaporate, so the actual thickness will be dependent on the solids content of the material. So in this example, I show a board assembly. It's been selectively coated, and now what's going to happen is we're using a wet film gauge, and we're going to place this on the surface of the printed circuit board. And when we lift the wet film gauge off of the surface of the printed circuit board under a UV light, we'll actually see where the coating is present on the gauge. And what you can see is those individual teeth on the gauge illustrate variations in thickness on the coating. And this is just a close-up view on the next slide. And here I show just two examples of gauges. And these are readily available, normally free of charge from a lot of vendors because it obviously has advertising on. But again, it's something you can buy or you can make yourself perhaps, and literally the teeth are contacting the board surface, the coating makes contact with that, and then you can see the coating on the tips of the terminations. Again, some people may consider this very archaic, but it's still something that's used in the industry today for checking the difference between coating thickness and also the dried coating after curing. Now, other things that you can do from a quality control point of view, and I think which are beneficial, is coat sample boards, but blank boards or blank substrates or test cards. And the reason for this is, first of all, find out the capability of your process. And this is particularly true in spray application. And with spray application, we are perhaps not aware of the thickness because we can't see it. So again, if we look at coverage and the quality and consistency of coverage, we know the capability of the machine before we actually move on to spray coating actual assemblies. And I show here an example of some test coupons as opposed to a test substrate or a test board. Now, test coupons are available from one particular vendor, but I'm sure it's something that you can make up yourself. And Nordson have been using these for many years, and what you're looking at in these three views are, first of all, a blank card and a card that's been sprayed, and it allows you to see the definition of the width of the spray. It allows you to see the stop start sequence, if there's any overspray on the surface when you put it under a UV light. So it gives you an illustration of the quality and consistency, and you can make a check of all the different parameters, i.e. the height of the nozzle, the solids content, the spray pressure, the materials you're using, all those different variables, and look at the performance. It is very, very difficult to do this investigative work on a board assembly which is covered with components. I know that's the real end result we need to do. However, it's also important to see the capability of your process before you actually start. And it's, again, something you can do at the start of a shift or after maintenance or trying out a new nozzle or new material. Again, it's relatively simple. Now, another thing which is important, and again, sometimes people forget to do this, is actually measuring the viscosity of the materials that you're actually using. And again, the manufacturer of the material gives you guidelines on the viscosity to use in manufacture. And this video clip will illustrate to you the simple viscosity check. And basically, what I'm showing you is measuring viscosity using a tool which is widely used in the industry. And basically what we're doing is filling up the container with a quantity of material, and what is happening is we're timing when we start and when the fluid stops or breaks. And by doing this, we can have an understanding of the relationship of solids content. And the suppliers, manufacturing suppliers, will provide graphs which allow you to compare your results with what might be expected. As an example, on this chart, I just show you 4 materials. This is Humasil products, and it shows you the time for the material, the stream to break, and the measurement in centipoise, the viscosity of the material. So again, suppliers will give you this information. Again, you're checking your material during regular monitoring. These are called Zane gauges, Zahn gauges. There are other automated methods of doing viscosity check, but this is a popular method which is used in the industry. Remember, we're measuring or checking the solids content of the material, and obviously if the solids content changes, just like with a liquid flux in wave soldering or selective soldering, it will affect the performance, and certainly in terms of conformal coating, it will affect the thickness of the material applied to the surface of a printed circuit board. Measuring the dry coating can be performed, and this is another thing to be considered, and there are different ways in measuring dry coatings. We can use thickness gauges, we can use microscopes that have a capability to do measurements, we can use labels that we can apply to the board, then remove them from the surface of the board, and check the dried coating thickness, subtracting the label thickness. In this example, what I show is a board, and it's actually got 3 labels on. Now, 2 of them have been put on the waste area of the board, and again, after coating, after curing, the labels could be removed and you check the thickness. Now, the thickness will vary on different areas of the printed circuit board, and as long as you know the relationship of both, then again you can use it as a quality control test. Again, you don't have to do all these checks. This is just an illustration of the different checks that you could consider running. With care, you can also do inline inspection, and inline inspection could utilize the UV torch that I illustrated earlier, or it could use the vision engineering mantis type system hanging over an inline conveyor system, or of course an automated AOI system. Now, if you're going to be curing the boards in an inline process in high volume or medium volume assembly, you probably will be using some form of IR oven to cure the boards. So it's just as important with conformal coating to make sure that when the boards are coated that you know what the actual profile is. So just like with reflow soldering, we're actually checking the profile. And I show you here a graph checking the profile for a proprietary coating. If you cure it too fast, what can happen is you'll form bubbles, and that's something you want to try and avoid. And just an illustration, some photographs I have here. This is a coating. It's quite a thick coating, as you can see. But if I were to speed up the curing of this coating and show you photographs of this, what you'll actually see is a lot of bubble formation. So you can see bubbles in the coating between the termination on this resistor network, and you can also see it between this SOIC. So something that we need to avoid during our curing process. So it's all in your control. When you speed up a coating curing process, this is one of the things that you can actually see, which is something we need to avoid. Inline curing can be in an inline process with a mesh belt, or it can be with pin transfer, just like a reflow soldering system. Again, it depends on the material you're using and the application. So we've gone through the inspection or some of the process that we can use, but just think about the criteria and also think about having the instructions available so it's clear to everybody, and also consider possibly a golden board as reference. So let's actually talk about the criteria now, and I'll mention the most common criteria. IPC 610 is the most common criteria that people use in industry. And I've illustrated the text from that standard here, and basically what we're looking for is a coating which is transparent, uniform in color and consistency, and uniform in thickness. But as we've already seen, you can get thin areas around sharp edges. Flat surfaces can be fairly uniformed. On the next slide, again, I've taken the text from the IPC standard, but because the standard has recently changed from D to Rev E, I've also highlighted changes. Now, there is not any radical changes, but they have removed some things. Like for the first red point, red text I show you, they've taken out loss of adhesion adjacent to masking. And what they mean here is the masking which is used to protect selected areas. But because loss of adhesion is covered in other parts of the standard, they've decided to make that simpler. They also coating in thin, but it's still coating component and device edges. Again, illustrated in another part of the international standard. Now, I show here some photographs in the next slide, and what I recommend to companies is they enhance the documentation that they have rather than just training to the IPC. IPC has defined the standards, but I think it's important to actually have illustrations of each of the types of defects that they talk about. And in here I show a number of examples. Top left hand is drainage mark, where the coating is draining down from a dip coating process. Center image, top row, shows cracking of a conformal coating. On the right hand top view we show fish eyes, and on the left bottom we show voids or bubbles in the coating. This is due to fast curing, probably. We show flaking or cracking of the coating in the bottom center view, and then foreign matter, foreign debris on the surface on the right bottom view. The point is, so everybody is clear what we're talking about when we're talking about defects or criteria for those defects. On the second group of slides, I've illustrated again some of the other issues highlighted. On the center area that we're seeing mealing, where the coating is slightly lifting on the edges. Top right hand view is contamination on a component, on a connector, and this is easily seen with UV light. Bottom left hand view, I show de-wetting of the surface, and literally this is where the coating is wetting small areas. It's been coated, but then it's pulled back. It's just like solder de-wetting on a printed circuit board pad or component termination. And then contamination on connector pins in the second image on the bottom row. And again, just illustrated, what's happened here is capillary has allowed the material to penetrate through the body of the connector onto the pins, which would obviously affect the contact resistance. And finally, on the right bottom view, I show coating not adhering to the surface because of contamination, which was on the board assembly prior to the coating operation. So again, it depends on controls of those. The key thing with inspection is looking for good coverage on the whole of the printed circuit board. And one of the things that we do for inspection, which we've already previously mentioned, is through the use of ultraviolet. And this video clip just shows an operator inspecting a printed circuit board assembly under ultraviolet light. And basically what he or she is doing is scanning the whole board assembly and comparing it with whatever instructions or golden board or inspection criteria is available. And in this particular assembly, there are a number of areas where masking has protected the board assembly, so some areas are free of any coating material. Again, it's having the space inspection capability available to allow you to do this. Now, thickness of coatings is something that can be quite difficult to actually do in practice, but if you are going to do thickness measurement, there are guidelines within the IPC, as I mentioned earlier, and I've illustrated them here. On the right-hand view, this is just a couple of test plates which have been produced, and what has happened is somebody has actually measured them, so they're now a calibrated reference source, and the numbers which are marked on here illustrate the thickness. And what can be done then, by using a digital measuring gauge, we can actually measure the surface and see what results you can get from the calibrated sample, and then you can use that to measure a reference board. Now, eddy current measuring systems are available in the industry, but it's important to realize that an eddy current needs a metal surface as a backing reference. Not all systems are the same. However, you need to try out the different systems to see the performance you can get. Now, this type of measurement is always done on a dry coating. You would never do this on a wet coating. If you did, unfortunately, somebody would be very unhappy because the gauge head may well be contaminated and be damaged. Now, at the start, I also mentioned some other standards which are available in our industry, and this is the NASA inspection criteria. Now, if you do a search on Google or another search engine, you'll find the NASA inspection standards, and these basically are for solder joints, assembly, and obviously, as we're talking about coatings, they cover coating of printed board assemblies. They also cover staking and potting of assemblies, but primarily they cover coating. So looking at these and the basic criteria. Now, in the criteria, it generally follows the IPC standard for coating. But again, it's probably more illustrative than some of the other standards which are available. So again, it's worth reviewing these. And I just flicked through a couple of pages of the NASA standard to give you an insight to what the document looks like. And again, you can review this at your leisure when you receive a copy of the slides, or when you search for the NASA criteria online. Now, in terms of process defects, in terms of soldering, but also in terms of conformal coating, one of the things that we've recently introduced at the National Physics Laboratory, where I also work with Dr. Chris Hunt, we've created an online defect database, which is something that you can use yourself to look at defects and also submit defects to get an answer to what might be the potential reason for them. And I'm showing you an example of the front page where you can actually select different search criteria. So if you were to put in, let's say, conformal coating and bubbles, or conformal coating and corrosion into one of the search strings that's available, and these are selected from the pull-down menus associated with each of the topics, which I illustrate, you'd be able then to look at illustrations. Now, what I show you here on this slide is we've actually pulled up a number of photographs from the database, and then you would select which one looks like the particular defect that you are currently investigating. The next step, you would select one by just clicking on the defect type or the photograph, and that would take you to another screen in the database. In this particular case, I've selected for this illustration a defect on conformal coating, and this is actually cracking of the coating. And on this screen you can read what has actually happened, the possible causes, where it actually happened in manufacture, and potential corrective action. And the nice thing is we can look at whether it's a high volume problem, a small volume problem, or in fact what type of product. Is it medical application or is it something else? And finally, you can click on the button again and you can blow up the screen much larger in size, which allows you then to print this out with the other information and pass it along to production staff or engineers on the shop floor as part of a corrective action. So again, the database obviously grows month by month, but the important thing is obviously putting in information which allows the quantity of information to increase for those people wanting to use it for failure analysis. So that's a sort of database. Now, going back to some of the illustrations that I previously showed you on different joints, and again giving you an understanding of what different joints look like after conformal coating, I'm illustrating here a J-lead termination, and here we've got again what I consider to be satisfactory coating using UV light again of a PLCC, a J-leaded package, and again you can see the glow of the conformal coating. If we look at the J-lead terminations and rotate it ever so slightly, at some point at this magnification you will see some surfaces that don't appear to be coated. If you're looking at high magnification with UV light, this could be down to the reflection as well. So it might appear there's no coating there, but by rotating it slightly you'll see, using the UV light, whether it is there or whether it isn't. Remember that this type of high magnification inspection is really after you're doing some sort of analysis of specific defects. At board level, as I illustrated earlier, you're scanning the whole of the board assembly using simply your eyes rather than using high magnification. You're using a higher level of magnification as you move into some sort of failure analysis. Now, in this illustration, this photograph, I show a PLCC again, a plastic leaded chip carrier, but you can see here that the coating does not appear to be present on the edges of the plastic. Now, this is a common thing which happens in conformal coating. On some plastic components, you can get poor coverage or even de-wetting on the surface due to the mold release compounds that are in the plastic packages as part of the fabrication process of the components. Now, in this example, it's just simply because you've got sharp edges. You can see good coating coverage on two sides, but not right on the edge. But sometimes you'll actually get de-wetting as well. A BGA component, if you're dip coating or you're spray coating, you won't guarantee to get coating underneath the device. In fact, some companies do not want to get coating underneath BGA style components. But here you can see in this view we've got 100% coverage, and as we move down to the second example, again you can see 100% coverage, even coverage on the sharp corners of the plastic molding on the BGA. But if we were to look underneath the package, you'll see that there is no coating underneath the package. You've got to decide on what is actually needed, and really that's down perhaps to development and design engineers to decide whether a coating needs to be underneath. And again, there is positives and negatives for doing this, as you probably can appreciate from a rework and repair point of view. The next couple of examples I wanted to show is going back to the Parylene coating, and I said that with the Parylene coating it is very, very difficult to actually see. In fact, in my opinion, quite often if you're talking about a 10 micron or a 15 micron coating, it's virtually impossible to see. But one of the ways you can do this is by actually putting if your boards are going to be coated with this material, you can actually put a very, very small dot inspection label on prior to coating, and then take the coating, take the label off, and then you can see the difference in visual appearance on the solder mask of the board with and without the coating. And also, if you're using a light measuring microscope, you can actually measure the thickness of the deposit from the top of the coating down to the solder mask. And this is something which would work quite nicely. Again, another example of Parylene, and virtually no evidence of the coating present. And just to illustrate the image that I showed earlier on about the coverage capability of this gaseous process, and this photograph shows the grey line around the PLCC where it's 100% coverage. 100% coverage. So, just to illustrate, if you're going to have different photographs, different illustrations to aid your inspection, this is something you need to consider. And what I show you here is just a few different types of defects. Now, here we see coating which is not covering all this row of capacitors. Now, in my opinion, just because there's a coating not present on the top of this particular capacitor, I generally would consider this is not a major issue. The key thing is the conductive interfaces on tracks, on pads, etc. But again, this is a personal view. Again, you in your own company need to decide on what is a defect and what isn't. Here we see bubbles forming around a component. Now clearly those voids and bubbles are between the package, terminations and other via holes on this particular product. So there is no insulator of any form. So this, in most people's opinions, would be unacceptable. If you look at this example, this is a QFP, quad flat pack. And on the quad flat pack you can see the coating is present around all the terminations between the pins. However, it's not coated properly on the QFP top body. Now, again, is this going to actually affect the performance of the device? I would suggest probably not, because the functional areas of the printed circuit board are covered correctly.